Hello, welcome back. I'm John, an old tired YouTuber. It's Wednesday today. I got my pension, but I have to wait for tomorrow, 1st September, to pay my bills. It's Wednesday 31. So I was out shopping 2 times. Today this little discount supermarket. I've not spent money from one of my MasterCard credits, so I have a little bit more money every month from tomorrow. And I'm not spending money on my MasterCards this whole next September. Then I will have like $8 or $9 more. October. Yes, I like to continue reading about the computer memory. Yes, I have a Danish video I need to put public. We need to get a little bit more to drink. So I was out shopping some fresh breads. Now the camcorder's out of focus. And I try even more candy, tomato, cucumber, some cola and cheese. Yes, but let's take some juice. I'm a little bit tired today because it's end of month. I got my money today, but I need to pay my bills tomorrow. Yes, I forgot to tell that. I have buy one more computer. I buy one more old second-hand computer. So I will get that in like next week. So let's read about the different kind of computer memory. I like to read it myself, but I'm not much I don't understand, of course. I don't understand everything because it's very high level technical information, and I don't have a university degree in computer science or computer engineering. But I like to read it anyway. Yes, I need to put this Danish video public and add it to my playlist. Yes, I record a Danish video every day about this war in Ukraine. I did that 189 days, soon 200 days. So actually I'm done for today. Yes, I'm updating the front page Danish news. Good. Let's start reading. But I should watch Netflix later. Yes, let's raise the sound level. And actually I would like to read everything here. about the memory. Yes, I need to adjust my camcorder a little bit, like this. Now that's the static RAM. So I have to write it down. Now my pencil is gone again. Looking for this pencil there. It was on my small desk in my bedroom. That's the McAfee. I have to renew. Static random. Access. Yes, just write it down there. Let's start. I have to look. I have to adjust the camcorder a little bit. And even more. Yes. And it's very hot in my living room again. And I'm a little bit tired, so I need half a minute to do myself ready. And I have to check my cell phone. Good, let's continue.
Static Random Access Memory. A static RAM chip from a Nintendo Entertainment System clone. 2K 8 bits. Static Random Access Memory, static RAM or SRAM, is a type of random access memory, RAM, that uses latching circuitry, flip-flop, to store each bit. SRAM is volatile memory. Data is lost when power is removed. The term static differentiates SRAM from DRAM, dynamic random access memory, which must be periodically refreshed. SRAM is faster and more expensive than DRAM. It is typically used for the cache and internal registers of a CPU, while DRAM is used for a computer's main memory. Contents. History. Characteristics. Applications and uses. Embedded use. In computers. Hobbyists. Types of SRAM and volatile SRAM. Pseudostatic RAM. By transistor type. By flip-flop type. By function. By feature. Integrated on chip. Design. SRAM operation standby. Reading. Writing. Bus behavior. Production challenges. Research. See also. References. History. Semiconductor bipolar SRAM was invented in 1963 by Robert Norman at Fairchild Semiconductor. 1. MOS SRAM was invented in 1964 by John Schmidt at Fairchild Semiconductor. It was a 64-bit MOS P-channel SRAM. 2. 3. The SRAM was the main driver behind any new CMOS-based technology fabrication process since 1959 when CMOS was invented. 4. In 1965, 5. Arnold Farber and Eugene Schnig, working for IBM, created a hardwired memory cell, using a transistor gate and tunnel diode latch. They replaced the latch with 2 transistors and 2 resistors, a configuration that became known as the Farber-Schnig cell. In 1965, Benjamin Augusta and his team at IBM created a 16-bit silicon memory chip based on the Farber-Schnig cell, with 80 transistors, 64 resistors, and 4 diodes. Characteristics. Though it can be characterized as volatile memory, SRAM exhibits data remainance. 6. SRAM offers a simple data access model and does not require a refresh circuit. Performance and reliability are good and power consumption is low when idle. 7. Since SRAM requires more transistors per bit to implement, it is less dense and more expensive than DRAM and also has a higher power consumption during read or write access. The power consumption of SRAM varies widely depending on how frequently it is accessed. 7. Applications and uses. SRAM cells on the die of a STM32F103VGT6 microcontroller are seen by a scanning electron microscope. Manufactured by ST Microelectronics using a 180 nanometer process. Topology of the cells is clearly visible. Embedded use. Many categories of industrial and scientific subsystems, automotive electronics, and similar embedded systems, contain SRAM, which in this context, may be referred to as SRAM. 8. Some amount, kilobytes or less, is also embedded in practically all modern appliances, toys, etc. that implement an electronic user interface. SRAM in its dual-ported form is sometimes used for real-time digital signal processing circuits. 9. In computers. SRAM is also used in personal computers, workstations, router sound peripheral equipment, CPU register files, internal CPU caches and external burst mode SRAM caches, hard disk buffers, router buffers, etc. LCD screens and printers also normally employ SRAM to hold the image displayed, or to be printed. SRAM was used for the main memory of most early personal computers such as the ZX80, TRS-80 Model 100 and Commodore VIC-20. Hobbyists. Comparison image of 180 nanometer SRAM cells on a STM32F103VGT6 microcontroller as seen by an optical microscope. Hobbyists, specifically home-build processor enthusiasts, 10, often prefer SRAM due to the ease of interfacing. It is much easier to work with than DRAM as there are no refresh cycles and feed dress and data buses are often directly accessible. In addition to buses and power connections, SRAM usually requires only 3 controls: chip enable, CE, write enable, WE, and output enable, OE. In synchronous SRAM, clock, CLK, is also included. Types of SRAM. Non-volatile SRAM. Non-volatile SRAM, NVSRAM, has standard SRAM functionality, but they save the data when the power supply is lost, ensuring preservation of critical information. SRAMs are used in a wide range of situations: networking, aerospace, and medical, among many others. 11. Where the preservation of data is critical and where batteries are impractical. Pseudostatic RAM. Pseudostatic RAM, SRAM, has a DRAM storage core, combined with a self-refresh circuit. 12. It appears externally as slow as SRAM, albeit with a density /cost advantage over true SRAM, and without the excess complexity of DRAM. By transistor type. Bipolar junction transistor, used in TTL and DCL, very fast but with high power consumption. MOSFET, used in CMOS, low power and very common today. by flip-flop type, binary SRAM, ternary SRAM, by function, asynchronous independent of clock frequency, data in and data out are controlled with address transition. Examples include the ubiquitous 28-pin 8K8 and 32K8 chips, often but not always named something along the lines of 6264 and 62C256 respectively, as well as similar products up to 16-bit per chip. Synchronous all timings are initiated by the clock edges. Address, data in and other control signals are associated with the clock signals. In the 1990s, asynchronous SRAM used to be employed for fast access time. Asynchronous SRAM was used as main memory for small cache-less embedded processors used in everything from industrial electronics and measurement systems to hard disks and networking equipment, among many other applications. Nowadays, synchronous SRAM, for example DDR SRAM, is rather employed similarly to synchronous DRAM. DDR's DRAM memory is rather used than asynchronous DRAM. Synchronous memory interface is much faster as access time can be significantly reduced by employing pipe architecture. Furthermore, as DRAM is much cheaper than SRAM, SRAM is often replaced by DRAM, especially in the case when a large volume of data is required. SRAM memory is, however, much faster for random, not block/burst, access. Therefore, SRAM memory is mainly used for CPU cache, small on-chip memory, FIFOs or other small buffers. By feature. Zero bus turnaround, ZBT. The turnaround is the number of clock cycles it takes to change access to the SRAM from write to read and vice versa. The turnaround for ZBT SRAM's auth latency between read and write cycle is 0. Sync burst SRAM or synchronous burst SRAM, features synchronous burst write access to the SRAM to increase write operation to the SRAM. DDR SRAM synchronous, single read/write port, double data rate I/O. Quad data rate SRAM synchronous, separate read and write ports, quadruple data rate I/O. Integrated on chip. SRAM may be integrated as RAM or cache memory in microcontrollers, usually from around 32 bytes up to 128 kilobytes, as the primary caches in powerful microprocessors, such as the x86 family, and many others, from 8 kilobytes, up to many megabytes, to store the registers and parts of the state machines used in some microprocessors. See register file, on application-specific integrated circuits, ASICs, usually in the order of kilobytes, and in field programmable gate arrays, FPGAs, and complex programmable logic devices, CPLDs. Design. A 6-transistor CMOS SRAM cell. WL word line. BL. Bit line. A typical SRAM cell is made up of 6 MOSFETs, and is often called a 6T SRAM cell. Each bit in the cell is stored on 4 transistors, M1, M2, M3, M4, that form 2 cross-coupled inverters. This storage cell has 2 stable states YK are used to denote 0 and 1. 2 additional access transistors serve to control the access to a storage cell during read and write operations. In addition to 6T SRAM, other kinds of SRAM chips use 4, 8, 10, 40, 80, 10T SRAM, or more transistors per bit. 13, 14, 15, 4-transistor SRAM is quite common in standalone SRAM devices, as opposed to SRAM used for CPU caches, implemented in special processes with an extra layer of polysilicon, allowing for very high resistance pull-up resistors. 16. The principal drawback of using 4 SRAM is increased static power due to the constant current flow through one of the pull-down transistors, M1 or M2. This is sometimes used to implement more than one read and /or write, port, which may be useful in certain types of video memory and register files implemented with multi-ported SRAM circuitry.